Hi guys, today I would like to talk about optics and imaging geometry. The slide that you will see, they are a part of my master degree that I was graduated from Finland. So this slide belongs to my graduation years, my studying years. So I would like to go through these slides and define it how you can actually select your proper lens or optics for your machine vision project. So why it is important to know a little bit basic and physics of illumination, because anyway it's save you a lot of cost, and you can prepare everything beforehand to go purchase anything so you don't have to give it back. That's why I go somehow fast through the slides, and we will see how effective that could be for you later by your comments. But to start this, I would like to thank my professor and lecturer at that time, Timo Prusi. I don't know if he watched my channel or not, but I'm really grateful and thankful for all this information that you provided for me. And yeah, let's start it. So optics and imaging geometry is the first step for you to begin your vision project. And it contains several things. So you have illumination, you have your object or your target, and based on your target you need to define or select a lens, and then you have to as well select the camera, and after that comes the software and computer, and then information for the user. So this is like a chain, and you have to somehow think what is the requirement from your customer side, and from the end just go backward and get to your optics, cameras, target, and illumination, and proper ones. So this is the way, as I said, you have to go backward from the end, what the customer needs, and then you will go step backward to select basically what is the computer software, what is the camera, what is the lens, what is the target, and what is the illumination. So the contents of this is that we will define a little bit what is the field of view, for example, what is the basics of the imaging geometry, what is the focal length, and then we will try to explain an example, and then the perspective and telecentric lens, the type of lens that are special. Then we will talk about resolution, light gathering ability, lens errors, particularly the distortion, some words about calibration, examples of common imaging setups, and so what. So what is exactly the field of view? Well, basically, when you are trying to capture images from an object, it depends that how big the field of view of the object is. If you consider that you need a brighter field of view, so the lens or the angle that the lens open up should be bigger. So as you see in this image, we have a camera like perpendicularly on a surface, which is our object surface, and then we define a square side as a field of view, and then we will define a work distance. So work distance, basically the distance between your camera and the surface or the plane that the object is. Let's say, imagine that the object is light flat, and it does not have it's not like it doesn't have a very big, it's not tall. So we can define a field of view. So the field of view does not necessarily means to be square, it could be also rectangular. So, and then we will talk about depth of field, which is basically the resolution that we are actually the maximum object depth that needs to be in focus at that time. The depth of field also is interesting for some application, if you want to focus exactly up the object, or if you want to consider also the background of the object. And then we will talk the size of the detector inside your camera, which is basically dependent on the application, and therefore optics also should match the detector size. And there are different type of optical connections, like C or CS mount, which basically C is an older version, CS mount is a newer version, and the resolution or a spatial resolution, which means that, well, basically whatever we get from this image is a 2D image, but the objects are 3D image, right? So resolution here, it means that what kind of proportions do we have from pixel values to the real values that are millimeter or centimeter. So these are the real values that everybody understands it. But when you say I have measured 10 pixels, nobody knows that. So you should define somehow an equation in a way to define the pixel value to the real values. So this means resolution. We will go through it back later. Then we will talk about the optical connections. As I said, the most typical connection are C and CS mounts, depends. I think this one I will skip because I have never seen in reality C mount optics anyway. Mostly are CS mounts. But for large detectors, you might want to need F mount like in Nikon, or K mount like Pentax optics, which are commonly used in photography. But basically for machine vision, you not need a big lens or with a very big focal length. So yeah, so the next, the selection of optics, size of camera detectors versus size of optics. So sometimes the optics are bigger than the detector modules or detector sensors from the camera, and sometimes detector sensor is actually bigger than the lens. So we want our optics to produce an image that is larger than the camera detectors usually. If not, parts of the image produced by our optics are not used. Vignetting or edges of camera image appear distorted and gradually fade to black if the size of the if the optics are smaller. The image should preferably be a little bit larger, since image distortion are larger at image edges. That's why we always want our image to basically to be bigger or larger as the camera detector. Otherwise, our image would be distorted, especially at the corner. For the optics, for the camera detectors, we have several different sizes, which are defined in inch format, and usually the aspect ratio is 4:3 aspect ratio between width and length. So width and height, that's basically. However, especially in modern cameras, the individual pixels are square. They have the same width and height, but it could be also the rectangular face. And the ratio between sensor size and the field of view is defined as magnification. How magnified is the camera optics combination. So basically, if you have a small sensor size and your field of view is very big, so you are magnifying this basically this image in a small size sensor. So that's why basically if your field of view is very big, you have a very low resolution. We will get to that later. Some background theory. Basically, there are different type of reflection. Sometimes light can be reflected from a surface quite nicely and, let's say, in a polarized way, and sometimes it's diffuse. So it's when it is specular, the reflection are very in order. But if it is diffuse, of course, every reflection will be back in a separate direction. And I think you know that when the light goes from one environment to another environment, let's say if the light goes from solid, not solid, let's say from fluid to the gas, definitely there is basically reflection and deflection, both reflection and deflection. Deflection because of the change of the environment structure, and reflection because of, and it's always when light hits some material, there's a reflection. Then this famous equation that you can consider that Ni and Nt, which are coefficients based on the refraction, or the index of refraction, and depends on the material that the light is going through. And theta I and theta t is basically the amount of angle that is actually based on the horizontal or vertical axis. So as you see in this photo, when you look, you see that it looks like this pen or pencil is broken, but it's not. Basically, it's just deflection of light. So you probably as well know the way that actually the curve interface surfaces can make or deflect the light. So that's the reason that there are a lot of lenses that can actually bend the light to a focal point. do not, it's either diverging or the other way around. I've forgotten the English name, but the lens can diverge or it can like indiverge. I don't know. So like this one, like the C one. So there are different type, different shape of lens. Then we get to very basic physics or theory of some background theory regarding object and the image. So basically, an object has x, y, z values in a real world as an object. Then we will make x, y, z axis, and the light of the objects will be comes through this lens and goes to this plane, a 2D plane that is basically our sensor plane in the camera, and it will be converted to x plane and y plane, which are basically the dimension of our object on this 2D plane. And then you have this f, which is your focal length or focal point, and then you have this distance, which basically the distance, your working distance, the distance between your object and your lens optics. So this model is called pinhole model. So here you see that there's equation is written nicely. So if you consider that, for example, f over z, z is the distance or working object, f is a focal, equals to r prime and r prime here is the distance from x prime and y prime to the center, and r here is the distance from x, y, z to this z axis, and it could be equal to x prime over x, y prime over y, and equal to r prime over r. So you can find the amount of or the value of x prime and y prime based on this equation, which is very simple. Well, basically, as I said, this is very important because robots, for example, if you are in your project, you have a robot, you cannot expect that robot to understand what is pixel. So you have to define it in millimeter or centimeter values, right? Here it's also another, when every time I would like to, I think about focal length, I would consider like a scissor, right? So it looks like a scissor. And when I decrease this angle, it means that I will decrease my field of view. And then it can also, if I extend the focal length, basically because your detector size is constant, so if I consider that my detector size is constant and I increase the focal length, slowly I will basically decrease the amount of angle. So my field of view would become smaller and smaller. But on the other way, if I increase my if I decrease my focal length, it will open up. So it will make my angle bigger. So I will see a broader field of view. This is a very simple way that to define the focal length and the field of view. So when you have a brighter, as I said, field of view, you have less resolution, and the other way around is opposite. Another equation between focal length s and s second. So s basically is the distance from object to the lens, and s second is the distance from lens to the image or your sensor. And you can use this equation to understand or to calculate your focal length. And then you have m, which is basically a proportion from h sec over h equals s second over s. So h second is basically the height of the image or the size of the detector sensor, and h is basically the object size, height or size. So these are all proportional based on the triangle theory. So if you want to, for example, select your optics for a value, you have to go with these options. Like, for example, you consider that I would like to consider my detector size to be 2/3 inch, right? Then I would say that my width value for my detector size is 8.8 millimeter, and my height would be 6.6 millimeter. If you use these two equation, considering these values for your detector size, then you will get two different focal lengths. So let's say if we use the height of the detector size, then we have a d, which is the working distance, and then we have h, FOV. So if I have my field of view of the object, it has a height and it has a width. So I would consider the h of my detector size multiply d over h FOV, and this will lead to like f, a focal length that I need to have to select my optics, right? But from this one you get one value, and when you consider the other one with the width and instead of height, the width value of your detector, and multiply it over by d and divide it over WFOV, then you will get another value. But always you decide to go to the shorter. So I think here it is also written. If the aspect ratio is not exactly the same as that of the detector, the two previous equations give two different value or focal lengths. Then the shorter of two calculated focal lengths is selected. Why? Because the shorter means basically the higher or bigger field of value. So you don't want to lose anything from your field of value, right? So then you can basically change your focal length, of course, field of value to change it. But basically you get one focal value smaller than the other one. So you have to always select the other one that is basically smaller or shorter. On the other hand, the focal length also sets the dimension of the smallest detectable features. So this has to be checked, right? You have to check if this is really the smallest detectable feature, in which focal length is more detectable. So because resolution is very important as well, you need to have a good resolution. If the previous focal length value do not give good enough spatial resolution, which is millimeter per pixel, the field of value has to be decreased or select a camera with high resolution. Yeah, so you have to select either a large field of view or a good spatial resolution. Lens manufacturer by default offer focal lengths of certain values 2, 4, 6, 8, 12, 16, 25, 50 or more. There are some lenses that are variable focal lengths that you can actually play with the focal lengths and find the right field of view, but they are more expensive, of course. Then you see that, for example, when you increase the focal length, the horizontal view angle, basically the degree decreases. So when you increase the focal length, you have a smaller angle and your field of view basically decreases. So here I think there is again some introduction of the lenses, type of lenses. We can play a lot with the lenses. We can define the focal length. We can like move the position of the focal length by putting different combination of the lenses basically. So these are like, for example, this one, you see how sophisticated and complex is when you are playing with too many lenses and from one place. I think, for example, in our smartphone cameras, there's a type of lens that called, I think, fish, or I don't know, fish eye, cat eye, I don't know. But there are some sophisticated that makes the scenery quite wide, so that you can actually take everything from a wide angle. So these are this type of lenses, as you see, like this one called Wild Avigon, Double Gauss, Zeiss, Artometer, Petzval, Cesar, Magnet, Telephoto, or Magnar Telephoto, and etc. So there are really different combinations of lenses. Then we will talk about the spatial resolution, why it is important, because as I said, imagine that you have taken a photo with, like, let's say 100 in 100 pixel, and when you compare it and when you look at the real object that you have taken, let's say the object is a tree which is like 10 meter, so you should say that for 10 meter image I have only 100 pixels. So how get that? It's like 100 over 10 meter, let's say 10 meter is like 100, yeah, 10,000 millimeter. So 100 over 10,000 millimeter, I would say that it is like, yeah, that would be like 10,000 to 1 over 100. So for 100 millimeter we have only 1 pixel, and that's not really good, because then you would say that every 100 millimeter or 10 centimeter you have one dedicated pixel. So if I can increase its number of pixel, I can zoom and I can see better, the quality of your image would be better, right? So you see, for example, the quality of the this value pixel over millimeter. Now you see how it is when you zoom, and so you have a lot of more pixel, and you can see the, especially for when you are defining your, when you need, for example, in your application to detect the edges or corners. So these are the values that the spatial resolution is very important. So you have to take care of that and consider that it needs really, you need a proper spatial resolution for your, as I said, either you have to increase the detector size and with more pixel values, or define smaller focal length in order to decrease the angle and focus on the small part of the object to have a high quality, not quality, high resolution. Just as an example, I would like to say, or define this example. Wanted FOV size is 4.5 millimeter. We want to measure the diameter of an approximately 20 micrometer diameter target. So our target is 20 micrometer, and the field of view size is 4.5 millimeter. Can we do it with 1 megapixel? It means 1000 camera. What about with a 4 megapixel camera? What is the spatial resolution for with both cameras, and how many pixels the 20 micrometer target covers? So this is also an interesting example. So basically, if the field of view is 4.5 millimeter, and we have basically 1000 pixel, the spatial resolution would be 4.5 micrometer per pixel. Basically, you have to see that you have to define millimeter over pixel, right? So the spatial resolution would be 4.5. So basically, yeah. So basically, so for 20 micrometer target covers less than 5 multiply 5 pixel areas. So you see that for, if the FOV 4.5 millimeter, and if you have just 1000, so you will define it to 5 pixel area, which in this case target can be detected, but measuring its radius, because it's basically not easy, because as you see that the borderline is really in the middle of nowhere of each pixel, so you cannot really measure its radius or diameter with any resolution. Is practically possible, right? But if you double the pixel, let's say if from 1 megapixel go to the 4 megapixel, which will be 2000 pixel each, then you have the spatial resolution around 2.25 micrometer per pixel, which means that 20 micrometer target covers approximately 9 multiply 9 pixel area. So yeah, now we have 1 2 3 4 5 6 7 8 9 10. So basically it's 10 to 10, but we say 9 area. But there is a important things here as the Nyquist value, that expected measurement resolution should be roughly always 2 times more than the necessary. So we should be at least 4.5 micrometer. The other way, we want to measure with 1 micrometer resolution. If we say that, okay, our micro, we want to be so small detecting object, then the spatial resolution should be at least half micrometer per pixel. And to cover up that wanted field of view, we need 4.5 millimeter divided by half micrometer per pixel, which a camera has 9000 in 9000 pixel camera. So it is 81 megapixel camera, I guess, which is huge, right? All right. I guess I would like to stop here, because I don't want to take it longer. So again, you see also as well here the accuracy values, how for the edge to be accurately located, the illumination has to be even around the edges, eliminate the shadows. And other factors are the quality of image, blur, autofocus, shadows, brightness, the image processing methods. These are also some values that are important to get a good valued image, in order that you can actually later do the post-processing and get or obtain information out of that. Alright guys, I hope that you enjoyed that, and please comment, share your thoughts, and let me if it is interesting, these topics for you. And next episode I will try to make other relevant topics regarding machine vision, automation, and etc. So similar. Alright, I hope that you enjoyed it. Bye bye.